Hello my dear students, welcome to the next lecture in Analog Electronics. In this lecture, let us discuss about feedback in amplifiers and the effect of positive and negative feedback. So first of all, what is feedback? It's a process of taking a part of the output signal and feeding it back to the input circuit. It has been found that this feedback is very useful in reducing the noise and making the amplifier operation stable. Depending upon whether the feedback signal aids or opposes the input signal, there are two types of feedbacks used. The first one is positive feedback, which is also known as direct or regenerative feedback, and the second one, negative feedback, which is inverse or degenerative feedback. So if the feedback aids, it is known as positive feedback. If the feedback opposes, it is negative feedback. Another classification is depending on what quantity you are taking as feedback. If you are taking voltage as feedback, it is voltage feedback. If current, then it is known as current feedback. So positive feedback. The feedback in which the feedback energy, that is whether either voltage or current, is in phase with the input signal. It is in phase with the input signal and thus aids it. It is called as positive feedback. Though the positive feedback increases the gain of the amplifier, it has the disadvantages such as increasing distortion and instability of the amplifier. So it is because of these disadvantages, positive feedback is not recommended for amplifiers. If the positive feedback is sufficiently large, it leads to oscillations. So you can see that positive feedback is utilized in oscillator circuits. Now what about negative feedback? The feedback in which the feedback energy, that is either voltage or current, is out of phase with the input and thus opposes it, is known as negative feedback. Though the gain of the negative feedback amplifier is reduced, there are many advantages of negative feedback. What are they? The stability of the amplifier gain is improved. Reduction is there in distortion and noise. There will be increase in input impedance and decrease in output impedance. And it also increases the bandwidth of operation of the amplifier. So because of these advantages, negative feedback is frequently employed in amplifiers, and we'll see some features. So this is the simple block diagram of a feedback amplifier. Here you can see it is negative feedback. The output V0 is fed through a gain beta to the input. So input is, the negative of the output is given. Here you see this is a negative. It is out of phase with the input signal. So it is known as negative feedback. Okay. Now there are different connection types of feedback. So there are basically 4 ways of connecting the feedback signal. Both voltage and current can be fed back to the input either in series or parallel. So there are 4 types of 4 combinations: voltage series, voltage shunt, current series and current shunt feedbacks. In this list above, the voltage refers to connecting the output voltages as input to the feedback network, and current refers to tapping off some output current through the feedback network. Series refers to connecting the feedback signal in series with the input signal voltage, and shunt refers to connecting the feedback signal in shunt or parallel with an input current source. Let us see one by one. This is a voltage series feedback connection. You can see the gain of the amplifier is, gain of the system is A equal to V0 by Vi. Now the feedback is given through a feedback network. This network is offering a gain beta. So this is V0 and this is the feedback signal. So Vf is equal to beta times V0 is connected in series with the input voltage. So this Vs is the input voltage and the feedback is connected in series. Since you are tapping the voltage, you are taking the output feedback from the output like this. So this is a voltage connection. Voltage is taken as feedback and connected in series with the input. It is a voltage series feedback connection. The next one you can see, it is voltage shunt feedback. That is again voltage is taken but it is connected in shunt to the input. So input is represented as a current source. So you need a current to be connected in parallel. So this network is offering a beta equal to If by V0, or this is the feedback current If. So this is voltage shunt feedback. It is connected in parallel or shunt, and again voltage is fed back from the output. Now this connection is giving you a current series feedback. So this current series feedback, you see, if you are taking current from the output, it has to be tapped from the output like this. Current is flowing in the circuit like this. So current is taken as feedback, and beta is again the gain of the network, feedback network, and it is connected in series. So of course you will have a voltage. So Vf is equal to beta times I naught is the current which is fed back. So beta I naught or Vf is connected in series with the input voltage. So it is current series feedback. Next it is current shunt feedback. Again current is taken as the feedback signal and it is connected in shunt with the input, which means here also you have a current. So beta is equal to If by I naught. So this is current shunt feedback. Now, what happens to the gain with feedback? So, voltage series feedback, you see, we are analyzing what is happening to the gain. If there is no feedback, then Vf is equal to 0. And the voltage gain of this amplifier is simply V0 by Vi, which is equal to V0 by Vs. Vi is equal to Vs if there is no feedback. If a feedback signal Vf is connected in series with the input, now Vf is connected in series with the input, then what is Vi? Vi is Vs minus Vf if feedback is there. Then V0 is equal to A into Vi, or what is Vi? Vs minus Vf. Substitute it here, you will get V0 is equal to A into Vs minus A into what is Vf? What is Vf in terms of V0? It is beta times V0. Substitute that beta V0 here. Beta V0. So you get V0 is equal to A into Vs minus beta V0. Or if you take beta V0 to the left side, you get AVs is equal to 1 plus A beta V0. That is written here. 1 plus beta A V0 equal to AVs. So that what is the overall voltage gain of this with feedback? AF. Suppose you call that gain as AF. AF is equal to V0 by Vs. What is V0 by Vs? A by 1 plus beta A. Or the gain is reduced by a factor 1 plus beta A. Or the new gain is A by 1 plus beta A. Now for voltage shunt feedback, again you will find the same expression. So it is AF is equal to V0 by Is here, because Is is the input. Then A into II by II plus If you do, and you simplify. How do you get this expression? This V0 is A into II. Then this Is is equal to II plus If if there is feedback. Is is II plus If. Substituting these, you get A into II by II plus what is If? If is beta times V0. Substitute that here, beta times V0, and finally you get an expression in terms of II, and again you get it as A by 1 plus beta A. So here also you see the gain is reduced by a factor 1 plus beta A. Now let us see what happens to the input impedance with feedback. If it is a voltage series feedback connection, this is a diagram which is a little more explained diagram with input showing the amplifier itself with its input impedance and output impedance. So here you see the input impedance can be determined like this. II is equal to, what is II? II is the input current. II is Vi by, this is II. II is Vi by Zi. So what is Vi? It is Vs minus Vf by Zi, or Vs minus beta V0 by Zi, or Vs minus beta AVi. What is V0? V0 is A times V. Suppose this is the gain of the amplifier. A times Vi by Zi. Now IIZi is equal to Vs minus beta AVi. Okay. Now Vs is equal to, what is Vs? This is the input voltage. So Vs is equal to IIZi plus beta AVi. Okay, from this expression. So so when you substitute this IIZi plus beta A Vi with IIZi again here, you get the new input impedance as ZIF is equal to Vs by II. This is Vs by II. What is the current? So this is the new input impedance as far as this circuit is concerned, because you have a feedback here. So you get Vs by II. So from this expression, Vs by II is this expression. You get Vs by II is equal to Zi plus beta A Zi. So that is written here, is equal to Zi into 1 plus beta A. Or finally you can say that the input impedance is increased by a factor 1 plus beta A. So the input impedance with series feedback is seen to be the value of the input impedance without feedback multiplied by a factor 1 plus beta A, and this applies to both voltage series and current series configuration. Whereas for voltage shunt feedback, if you analyze, then what happens to the input impedance with feedback, that ZIF is equal to, this is shunt connection. Voltage is connected, voltage is taken as feedback and connected in shunt. Here the input impedance is Vi by Is or Vi by II plus If. Substitute this these values here. This is beta V0. Then divide throughout by II. You will get it as Zi by 1 plus beta A, or in this case the input impedance is decreased by a factor 1 plus beta A. Next, output impedance with feedback. I am giving this as a second assignment question. So you may refer the books and submit it as an assignment. What happens to the output impedance with feedback? These analyses can be tabulated together, and we can finally conclude that for effect of each feedback connection on input and output impedance. Here you have the input impedance and here you have the output impedance. You see, for voltage series connection, the input impedance is increased. For current series also, it is increased by a factor 1 plus beta A. Then for voltage shunt and current shunt, it is decreased by a factor 1 plus beta A. What about output impedance? Output impedance is decreased for voltage series by a factor 1 plus beta A, and it is increased by a factor 1 plus beta A for current series, and for voltage shunt feedback it is decreased by a factor 1 plus beta A, and for current shunt it is again increased by a factor 1 plus beta A. Now this is a simple problem where you can determine the voltage gain, input and output impedance with feedback for voltage series feedback having A equal to minus 100, Ri 10 kilo ohm, R0 20 kilo ohm for a feedback of beta equal to minus 0.1 and beta equal to minus 0.5. So you see what happens to, for a voltage series, it is decreased, gain is decreased by a factor 1 plus beta A. So what is the new gain? A by 1 plus beta A. Substitute for A, beta and again A here, you will get that the new gain is minus 9.09. Okay. So the gain is decreased by a factor 1 plus beta A. Now see what happens to input impedance. For voltage series, the input impedance increases by a factor 1 plus beta A. Substitute the values, you will get the 10 kilo ohm is changed to 110 kilo ohm. What about the output impedance? You can derive these expressions. It is Z0 by 1 plus beta A, and you can see the output impedance is decreased by a factor 1 plus beta A, and you get it as 1.82 kilo ohm. Now do this problem for beta equal to minus 0.5. Again you will get these answers. The gain will decrease, input impedance will increase by a factor of 1 plus beta A, and output impedance will decrease by a factor 1 plus beta A. So we can continue our discussion on feedback in the next lecture. Thank you.